Hello, everyone. My name is Xiaoxia from Qualcomm Technologies. Today, I'm going to talk about the 5G private network foundation for Industry 4.0. As we know, 5G is accelerating globally. As of now, there are already more than 140 operators with 5G commercial deployment. And in addition, there will be more than 300 more operators actively investing in the 5G deployment. It is expected up to 2014, we will have more than 3.8 billion 5G smart devices to ship. If we look at a single year in 2022, it's expected more than 750 million smartphones to be shipped out. Actually, compare 5G with 4G, we can see that the 5G connections is much more faster compared to 4G. So by the year of 2023, there will be more than a billion 5G connections, and which is 2 years faster than 4G. The reason is that 5G is embracing multiple different vertical use cases compared to the 4G, and that's why its connection is penetrating much faster compared to the 4G. And also, there are more than 800 5G designs launched or in development across the world. Yeah, now let's take a look at the typical the future industry, where we can see that there are lots of use cases and diverse requirements in the industry deployment. So if we look at the head-mounted display, we can see that the data rate is very high, up to gigabits per second. On the other hand, if we look at the massive IoT, right, for the process monitoring, we can see that the data rate is not very high. But do keep in mind that you have to support massive number of such IoT devices. And now when we zoom into this motion control in the industrial robot, we're talking very high reliability and low latency. So the latency can be as low as 1 millisecond, and the reliability can be as high as 6 nines. So all these diverse use cases and different requirements in the industry 4.0, so those will be addressed with the 5G design and specifications. Now let's look at one of those features one by one. Start with the private network. So what does the 5G private network offer for the industrial IoT? So first of all, the private network allows us to deploy a dedicated local network where we can use dedicated resources that allows us to manage the network independently. Secondly, the private network allows us to achieve better security so that basically the sensitive data can stay on-premise without going to the public cloud. In addition, the private network allows us to have performance optimization for the target local applications. So for example, if we are looking for motion control in the industrial deployment, and we're looking for low latency and high QoS requirement in the 5G applications. So where we can deploy those techniques to achieve such a requirement. And in addition, the 5G is known to have a great interoperation capability. So because 5G is a global standard, it has a great ecosystem. So it's future-proof with a rich 5G roadmap. All the enhanced 5G feature, which will be developed in the future release, can be easily put in when we advance our system. If we look at the private network growth across the world, you can see there's a growing momentum across the world day by day, right? So some of the network, private network deployment you can see is assisted by the public network, while some of the private network deployment is a standalone private network without the public network assistance. Now let's look into some of the detailed 5G features to meet the industrial IoT requirement. So we already talked about the 5G private network. But the next question is that, yes, the solution of private network is great for 5G, but how do I deploy it? Where do I get the spectrum? So luckily, 5G includes all the diverse spectrum for people to deploy the private network. So ranging from the licensed spectrum, shared spectrum, and unlicensed spectrum. Especially with a standalone unlicensed spectrum, people can deploy the private network without the dependency on the licensed spectrum. And also there's a big range of the spectrum itself, ranging from the FR1, which people so-called the lower band, and to the higher band, the millimeter wave band. So because of all those diverse spectrum usage, people have a great flexibility in deploying the private network for 5G. Now, when we come to the data communication, recall that the future industry, we want to replace a wire with a wireless connectivity, right? So the data communication, the requirement has to match what people can achieve with a cable or the wire network. So the way the 5G achieved ultra reliability and low latency for the data communication is through the spatial technique, so that we can still maintain high reliability without going to the increased latency. Another important feature in 5G is the time-sensitive network, which ensures all the devices to maintain time synchronization so that we can have unified motion across a specific time. And that's very important for the future industry. Last but not least, the positioning. We know that for the factory automation in lots of applications, the positioning is essential. Without positioning information, lots of applications will not be feasible. So we will zoom into one by one in later slides to talk about all those features. Now let's take a look how the 5G connectivity can reform the existing industrial network. If you look at the existing industrial network, you can see that there are lots of devices, including the sensors, controllers, machineries, and those are connected through the wire. In the future, with the 5G connectivity, we're going to replace those wires with a wireless that allows us to add more nodes, replace the nodes, or move the nodes. And that basically offers us with a great reconfiguration capability of the future network for the industry 4.0. And in this deployment with wireless, we can also see that we actually have deploying multiple transmission and reception points. For a particular wireless link, if the signal gets blocked or faded, we can have the signal from the other transmission reception point that can still ensure the successful delivery of the packet to achieve the ultra reliability and low latency. Now let's take a closer look of how 5G brings the support of time-sensitive network. As we mentioned, that TSN in lots of cases is an important feature for the industry 4.0. So the way 5G ensures tight time synchronization is by having the TSN master clock, which propagates the timing information to the end TSN devices. And when the message goes through the 5G behaves as a TSN bridge. It records the incoming timing, and then when the packet goes out of the 5G, it will add the computation or the correction field that allows the TSN end device to correct the timing accordingly, so that all the devices can achieve tight time synchronization. When it comes to the positioning, the 5G supports a wide range of new vertical use cases. It includes a positioning for both indoor and outdoor. It also complements existing positioning technologies, such as GNSS, Wi-Fi, Bluetooth sensors, along with the 5G positioning technology. And then in addition, the positioning is targeting for lots of different accuracy and latency requirements for the diverse service requirement. So for example, in the RE17, we are working on the industrial IoT positioning that can support up to 20 centimeter accuracy, where for outdoor, you can have more relaxed accuracy requirement. Now let's take a look at how 5G achieves ultra reliability and low latency through the spatial technique. Traditionally, people in a wireless technology, when people try to achieve ultra reliability, the typical technique is through the diversity through the either frequency or time. However, those diversity scheme is achieved as an increased latency. So for example, we can use a retransmission to achieve higher reliability. However, the retransmission takes time, and which introduce additional latency. In lots of cases for the industry applications, we may not be able to afford to use extended latency for lots of applications. So the way 5G tackles the problem is by deploying multiple spatial techniques that you can see that there are multiple transmission and reception points. So when the blocker drives through, it may block a particular wireless link. However, the other link signal is still strong, and that allows the successful delivery of the packet so that we can achieve low ultra reliability and low latency at the same time. So indeed, the spatial technique COMP, the so-called coordinated multiple point transmission techniques, is facilitated by the dense deployment of the small cells in the industry deployment. Indeed, with such dense deployment, it is very useful, attractive for us to deploy the 5G technology in the millimeter wave band in a smart factory. So Qualcomm is collaborating with 5G ecosystem leaders to deploy 5G millimeter wave in a smart factory. So here we show a particular example where we have this manufacturing floor, which around 3,000 square meters, and then up to around 3.7 meter high. So in this case, we are deploying 5G non-standalone network where we have 400 megahertz downlink and 200 megahertz uplink in the 28 gigahertz band. Our measurement indicate that we can have medium throughput greater than 1.5 gigabits per second in downlink and more than 120 megabits per second in uplink. With such great throughput, we can support different use cases. So for example, the AGV, augmented reality, and as well as a virtual reality that we will use a lot in the industry applications. Indeed, the private network in 5G also drives new efficiencies and innovations with the integrated 5G private network and edge. So for example, with a 5G private network, we can have the sensitive data stays on the private edge to do the distributed edge processing that allows us to do the distributed AI, for example. We can also have the non-sensitive data going to the public edge, which allows us to do the cloud processing. Up to now, we have explained some of the 5G features which are essential for the Industry 4.0. Now let's look at some of the demos to showcase those 5G features. Let's start with the first demo, the factory of the future using 5G connectivity. In this demo, we have the Edge Cloud, which consists of COMP server and the PTP Grandmaster, in addition to GNOB 5G core and GPS. There's also OTA testbed, which consists of 4 transmission and reception points, and they are serving 4 different IoT devices. In this particular, in the beginning, we can see that there's no TSN enabled, and all the IoT devices are not synchronized. They have their own separate timing. And we can also see that there's no COMP enabled. In a sense, there's a single, the device is served by a single transmission and reception point, and there's no COMP. Once TSN is enabled, we have the PTP Grandmaster generate the source clock, and that timing information is sent from GNOB to TRP, and then TRP send the timing information to the individual IoT devices. In this way, all the devices can be synchronized up to a tight synchronization requirement. Why is a TSN important in the future factory? So let's look at some of the examples which we show here. With the TSN, it allows a synchronized control among all the devices. So in this particular case, we can see that we have the smart camera, which takes the photos of the objects, and then it uses onboard AI for object classification and recognition, and send that information to PLC. Once the PLC has this information, it will send a command to a robotic arm, as well as the gates, to perform the synchronized behavior. We also notice that we enable the COMP for both downlink and uplink, so that you can see that each device can get a signal from multiple transmission and reception points. So this allows that in case the wireless signal from a subset of TRP is getting faded or blocked, we still have this useful signal from the other TRP, which can ensure the successful delivery of the packet. Besides the TSN and COMP, we are also going to showcase how to improve the network efficiency and capacity and improve the latency by using the direct UE to UE communication. Let's zoom into the layout of the demo. So in this particular demo, we have 4 transmission and reception points, and then they are serving 4 devices. On network side, we have this high-performance computing platform used to support time-sensitive synchronization as well as a COMP for the ultra reliability and low latency communication. When we enable the TSN, we can see that all the timing synchronization across all the devices are within 0.1 microsecond. Recall the target accuracy requirement is 1 microsecond. And as a result, we can see that robotic arm doesn't miss any objects. On the other hand, if we disable the TSN, now we can see that now the timing synchronization error across the devices now goes up to 1 millisecond. And then because of this 1 millisecond accuracy error, we can see that oftentimes the robotic arm ends up missing the objects. We can also take a look at the SNR of the devices when we disable the ultra reliable communications. In this case, you can see that the SNR of the user is getting dropped significantly compared to the URLLC feature is on. And as a result, we do see a lot of packet goes in error when we disable the ultra reliable communications. Now let's take a closer look at the conveyor belt in the demo. So here we have multiple devices. We have the RB3 vision camera, which takes the photos of the objects and then uses the onboard AI for the object recognition and classification. And afterwards, it sends this information to the PLC. Then the PLC is going to send out a command to the robotic arm and gates to perform the synchronized behavior. Now let's take a closer look at the conveyor belt in the demo. So here we have multiple devices. We have the RB3 vision camera, which takes the photos of the objects and then uses the onboard AI for the object recognition and classification. And afterwards, it sends this information to the PLC. Then the PLC is going to send out a command to the robotic arm and gates to perform the synchronized behavior. Now let's zoom into how this demo behaves. So we can see that when we disable the TSN, it may miss the projects because of timing asynchronization across the different objects. So now this is a picture of the live demo. So we can see that robotic arm is picking up the objects and place them in different lanes based on the object shape. And then the gates open accordingly. Up to now, we have mostly been focusing on showcasing the ultra reliability and low latency communication, as well as the TSN for industrial IoT. Those are the 5G features which are essential for the Industry 4.0. One thing which we want to highlight is that in this demo so far, when device 1 wants to talk to device 2, the packet needs to go through the GNOB, which clearly motivates us to enable the direct device-to-device communication to further improve the system capacity and enhance the system efficiency. Now let's take a closer look on the Sidelink communication in the industrial IoT in the demo. Here we are also going to show the benefit of the Sidelink communications. As we mentioned before, without the Sidelink, when the two devices want to talk to each other, they have to send the information through the GNOB, and then GNOB sends the information to the other device. Here we can see that clearly this two-hop communication can be improved by enable the UE to UE Sidelink communications. As a result, because we use one-hop transmission compared to the two-hop, we can see that we only need to use almost half of the resources so that we can achieve better network efficiency and capacity. Let's also take a look at the IIoT capacity boost with the 5G Sidelink. In this particular layout, we have 18 GNOBs in a 50 meter by 120 meter layout. And by the way, this is a 3GPP indoor factory layout. And when we disable the Sidelink, when the PLC wants to talk to sensor actuator, we need to have two-hop transmission, where the first hop can come from PLC to GNOB, when the second hop happens between the GNOB to sensor and actuator. When we enable the Sidelink, we can see that the PLC can talk to sensor actuator directly. As a result, we can see that once we enable the Sidelink communication, we can achieve 1.8 times more capacity compared to the Sidelink is off. The second demo is on the 5G indoor precise positioning, where we are going to show that with 5G positioning signaling, we can achieve up to 20 centimeter accuracy, both horizontally and vertically.
So in this OTA demo, we are going to show the indoor precise positioning through the wireless 5G technology. So as we all know, the 5G is expanding into lots of new vertical areas. For example, industrial IoT. So in this early research, we're going to show in the OTA demo, we're going to show that how the precise positioning can help further to enhance the 5G application. In this particular use case animation, we're just going to show one example on how precise positioning is important in the industrial IoT application. So in this particular example, the industry worker sent a command to AGV, where the AGV, based on the command and the positioning, it navigates to the right aisle and pick up the items on the right shelf. Now, once the AGV pick up the right items, it will navigate also based on the help of the precise positioning to the docking station, where it's going to unload the system successfully. So let's now start look at the network layout. So in this test bed, we installed 5 TRPs, which stands for transmission and reception points. So let's take a look at the particular TRP. So each TRP is capable of transmitting with 4 TX antennas and receive with 4 RX antennas. So in this particular test, each TRP is sending the positioning signal, which spans 400 megahertz wide in an unlicensed of 6 gigahertz. In this test bed, we are using the positioning algorithm, which is called OTDOA, where the test device is estimating the position by using the observed time of difference of the positioning signal to the test device. So where you can see that we have the test device moving in this controlled environment, which is 12 by 16 feet wide. In order to compare the positioning error versus the true ground truth, so we actually installed a gantry system. So the purpose of a gantry system is to allow us to control the test device to move in a controlled fashion. And in addition, the gantry system can report the ground truth, which allows us to compare the ground truth versus the estimated positioning. Now let's start test of route 5. So where now you can see that now with the control of the gantry system, now the test device is moving in a route of 5. Let's switch to the 2D view, so that allows us to see better on the horizontal plane. So now you can see that the test device is moving with a trace of 5. So on this trace, the black dots represent the ground truth, which is reported by the gantry system, which represent the true location of the test device. And where the blue dots represent the estimation of the position based on our test bed. So you can see that those two lines, they track closely with each other. And the red circle represent the 30 centimeter tolerance. So all you can see that the area is way below the circle. So let's also take a look at the vertical accuracy, where you can see that, which is typical more challenging for the positioning algorithm. So even in the vertical domain, we can see that the area is much below the 30 centimeter as a target. So overall, let's look at the summary results. From the PDF file, we can see that there's no error beyond 23 centimeters. And then looking at the horizontal plane, that error is even much smaller. So even at the vertical plane, all the errors is way below 25 centimeters. So overall, our target accuracy is much better than the requirement. We can also start route 8, where we are going to stretch test how position algorithm works in a high-speed case. The test device is going to travel through 8 corners controlled by the gantry system. So every time when the test device starts with a corner, it tries to speed up. And then when it moves to a corner, it tries to de-accelerate. So every time you see there's a big speed change, so which creates more challenging situation for the position algorithm. But even in those situations, we can see that the error is below the 30 centimeter accuracy. To conclude, so in this OTA demo, we have shown our early 5G research in the precise positioning. So the precise positioning will be part of Release 17 study. So we will be using our OTA demo to support our research and the standards activity in the Release 17 studies.
With that, I would like to conclude my presentation. Thank you for your attendance.